Hi, I'm Yupeng Liu, Development Engineer within the Radio Transceiver Multi-Market Platform Group at Analog Devices. In this video, I'm planning to introduce you the ADRV9002 Agile Software-Defined Radio. The ADRV9002 is a dual-channel, narrowband and wideband RF transceiver platform. It is our first high-performance narrowband and wideband, single-chip, TDD and FDD, highly integrated transceiver. It contains two independent receivers and transmitters, and two independent on-chip RF local oscillators that can be routed to any of the transceiver or receivers. The radio provides a wide RF tuning range from 30 MHz to 6 MHz. RF bandwidth is highly scalable from 12 kHz to 40 MHz per channel. It offers user-configurable serial LVDS or CMOS data interface. The radio incorporates advanced signal correction algorithms and tracking calibration algorithms. The ADRV9002 offers a number of advanced system features such as fast profile switching for dynamic data rate and sampling rate, flexible power control versus performance control within both analog and digital circuits, a monitor mode to optimize system power consumption, multi-chip synchronization, fast frequency hopping, digital pre-distortion for both narrowband and wideband waveforms. It also offers a number of useful auxiliary system and control functions to aid customer design. Now, I'm going to hand it over to my colleague Hyman to show you the RF performance of this chip.
Thanks, Yupeng. Hello, and my name is Hyman Shannon. I'm a principal RFIC design engineer with Analog Devices. And today we're going to show you some of the key RF performance metrics for the ADRV9002. So let's start with the receiver. The ADRV9002 has the highest dynamic range on the market today, from 30 MHz to 6 GHz. It achieves exceptional phase noise and blocker rejection performance. The receiver has both zero and IF down conversion capability. In an IF down conversion mode, the desired signal, its image, and any other blockers are down converted to an IF in the digital baseband. The desired signal is extracted, the blockers are filtered, and the image is rejected, all in the digital domain. This is thanks to the true software-defined nature of the ADRV9002. Using this IF mode, we are going to input an 8 kHz signal at -108 dBm, and we are going to sweep this large continuous wave blocker next to it in a frequency and amplitude to get to an SNR of 7 dB. The receiver achieves in excess of 98 dB blocker rejection in this test, with an image rejection of about 86 dB. A key metric in a high dynamic range receiver is phase noise. So let's have a look at the phase noise performance of the internal LO of the ADRV9002. With the device clock connected to a 38.4 MHz Windsor cluster oscillator, this is the phase noise at 470 MHz LO. Another key feature on the ADRV9002 is the transmitter digital pre-distortion, or DPD. This is a block diagram of a DPD test setup where the transmitter output signal is fed to a PA using a variable attenuator and a harmonic filter. A coupler with 30 dB attenuation feeds back a portion of the PA signal to one of the RX inputs on the ADRV9002. This is done through a splitter, where we can also observe the PA output on a spectrum analyzer. One of the profiles on the ADRV9002 is the LAN mobile radio tetra profile. Here we are looking at a 50 kHz tetra signal at the P output without DPD. We can see that the adjacent channel power ratio, or ACPR, is 45 dB. But once we enable DPD from the GUI, the ACPR drops to 75 dB, which is a big improvement. The ADRV9002 achieves its RF performance with an array of power-saving modes. This is the power consumption of the ADRV9002 in sleep state. You can get this information from the GUI. You can put the transceiver in RX state and you can also observe its power consumption, as well as TX state. We hope this video gave you an introduction to the RF performance of the ADRV9002, and for more information, please visit us at analog.com/ADRV9002. And thank you.